Good afternoon. During the last lecture, I introduced the definition of a second fundamental form as the quadratic form associated to the Weingarten map. It is denoted by this symbol, and it is defined this way for any vector v in TPS. Now, I want to present the consequence of proposition definition 4.8. So if V1, V2 is an orthonormal basis of TPS, of eigenvectors of WP with the corresponding eigenvalues K1 smaller or equal to K2, then if V is in TPS and its length is equal to 1, then I can write V as cosinus of theta V1 plus sinus of theta V2. The second fundamental form evaluated at V is equal to K1 cosinus square theta plus K2 sinus square of theta. And we also saw that the Gauss curvature P has been defined as the determinant of the matrix which represents this map. It is equal to K1 times K2, and the mean curvature at P, it is 1/2 the trace of the matrix representing this map. That is 1/2 K1 plus K2. Let's present one example. It is the example of a cylinder of radius r. So we denote the cylinder of radius r by CR. This can be defined as follows. The set of points of coordinates r cosinus of theta, r sinus of theta, z in R3 such that theta varies in 0 to pi and z is a real number. It's easy in this case to find a unit normal vector field. Precisely the unit normal vector field which is outward pointing is given by this formula, and at P is equal to cosinus of theta sinus of theta 0 at the point P of coordinate r cosinus of theta r sinus of theta z. This formula is intuitively clear. If this is our cylinder, this is the z-axis, then it is clear that if this is the point P, n of P is an horizontal vector, so the last component is equal to 0. And in order to find the first two components, it's enough to work with a circle that you get if you intersect the cylinder with the horizontal plane passing through P. The circle that you get will have radius r, and we know already that the normal vector okay, let's write normal vector at Q of a circle of radius r. It is Q divided by the length of Q, that is Q over R, where Q is R cosinus of theta, R sinus of theta. If you replace Q into this formula, you will get exactly the first two components of N. Now, let's observe this picture, and let's try to find what are the values of K1 and K2. So previous remark says that K1 is a smaller possible value for the second fundamental form evaluated at a vector of TPS of length 1, and K2 is the largest possible value. On a cylinder of radius r and a straight axis, there are two spatial curves. There are circles like this, for which it's easy to find the curvature, and there are straight lines, vertical straight lines like this. Also in this case it's easy to find the curvature, and the respective values will be minus 1 over r and 0. It is intuitively clear that if we consider any other curve passing through P and which is not equal to a straight line or a circle, for example a curve like this, we will get a value of the curvature which is contained in the interval k1, k2. So at least from an intuitive point of view, it is clear that k1 is minus 1 over r and k2 is equal to 0. So what is the orthonormal basis of TPS, which is convenient to use in this case? It is convenient to use, let's use the white color. It is convenient to use V1 given by the tangent vector to this circle, and V2 the tangent vector to this straight line. Precisely, V1 is given by minus sinus of theta 0 cosinus of theta 0 0 if P is a point of coordinates cosinus of theta 0, r cosinus theta 0, r sinus of theta 0, z0, and V2 0 0 1. They are clearly of length 1 and orthogonal, so they are an orthonormal basis of TPS. Now let's try to make the computation of the curvatures. In order to find W P V1, that is minus dn P V1, sorry, I made a mistake. I was writing down the formula for the second fundamental form. I need only to write minus n compovi gamma prime 0, where gamma is a regular curve with gamma 0 equal to P, gamma prime 0 equal V1. So for example, you can choose gamma t to be r cosinus of theta 0 plus t over r, r sinus of theta 0 plus t over r, z0. This is a regular curve on the cylinder, precisely is a circle. The reason why you have t divided by r is that you want to work with the curve which is parameterized by arc length. And if you make this computation, you will find that WP V1 is equal to minus 1 over r v1. Instead, if you want to compute Wp at v2, you have to use this formula, where gamma tilde is a regular curve on the cylinder with gamma 0 equal t, gamma prime 0 equal v2. In this case, we can choose gamma tilde t equal r cosinus of theta 0, r sinus of theta 0, z0 plus t. And if you make this computation, you will find that Wp v2, this is equal to 0 times v2. So this says that v1 equal minus sinus of theta 0, cosinus of theta 0, 0, and v2 equal to 0, 0, 1, are principal direction and the principal curvatures are k1 equal minus 1 over r, k2 equal to 0. Consequently, the Gauss curvature at t is given by k1 times k2 equal to 0, and the mean curvature h at t given by 1/2 k1 plus k2 is a minus 1 over 2r. Now I want to present an alternative characterization of the normal curvature. I want to recall what is normal curvature. If V is a vector in TPS of length 1, then the second fundamental form of S at P evaluated at V is the normal curvature of S at P in the direction of V. So as I announced, I want to present proposition 4.11, which gives us an alternative characterization of the normal curvature, and this also provides us with an explanation of the name, why we call this number the normal curvature. So let S be as usual an oriented regular curve, P be a point of S, V a vector in TPS of length 1. Then what we do now is the following. We consider the family of all regular curves gamma in S with gamma 0 equal to P, gamma prime 0 equal V, then 1 for every curve gamma. We have that the normal curvature, it is given by this inner product this formula says that the normal curvature is nothing but then the normal component of the initial acceleration of gamma to the minimum curvature at P among curves in this family regarded as a space curve equals the absolute value of the normal curvature. Before giving you the proof, let's make a remark. The remark is about this formula. The right hand side depends on the second derivative of gamma. Instead, the left hand side depends only on V, which is the initial derivative of gamma. So the remark is the following. Surprisingly, the product gamma second 0 and P does not depend on gamma second 0. Why? Because the left hand side depends only on gamma prime 0. And now let's see the proof. So our goal is to prove this formula. Unfortunately, I have to write something. Let's maybe copy the formula here. Okay, let's observe that gamma prime t is orthogonal to n evaluated along gamma t. Why? Because this is a curve, this is a derivative of the parameterization of a curve on the surface S. So this is a vector of t gamma ts. Instead, this is a normal vector, so this is always orthogonal to this one. Consequently, if I take this product, this is always 0. This means that also this derivative is 0. Now, what happens if I compute this derivative? This is equal to gamma second tn. Sorry, I made a typo. So instead of writing n of t, I should have written n gamma t times n of gamma t sorry, I had to erase the formula, plus gamma prime t multiplied by n dt n gamma t. Now, what happens if we evaluate both sides at t equals 0? We get that 0 is equal to gamma second at 0 multiplied by n evaluated at gamma 0, but gamma 0 is p. So I can write just n at p plus the product of gamma prime at 0, but gamma prime at 0 is v, so I can write v. And what is this? In order to compute this derivative, you have to use the chain rule, and then you have to evaluate at 0. So you get dn evaluated at t equals 0 gives you dn at p gamma prime 0, which is v, but dnp evaluated at v is nothing but then minus wp at v. Now we observe that v multiplied by minus wpv is exactly minus the second fundamental form of S at P evaluated at V, and we get that the second fundamental form of S at P evaluated at V is exactly this. So we prove this formula. This formula justifies the name of normal curvature, which we gave to the left-hand side. Because here we take the normal component of the initial acceleration vector. Now we have to prove the second statement of proposition 4.11. Okay, let's observe that the curvature K at P of an arbitrary curve gamma in this family is the norm of the component of gamma second 0, which is orthogonal to V. This implies that we have this inequality. The absolute value of this number is smaller or equal to K. Now, we already know that this number is the second fundamental form evaluated at V. In order to prove the second statement, we have to prove that this lower bound is achieved. In other terms, let's show that this lower bound is achieved. In other terms, we have to show that there exists a curve gamma for which gamma second at 0 is parallel to n at p. Let's see how to construct this curve. We use the same construction as the one of exercise 3.67. So we consider the subspace P defined to be the span of V and N at P. Then we have that the intersection of P plus capital P. When I write this way, I mean the translation of this subspace to the point P. This means that the origin of this subspace now coincides with the tip of the vector, the position vector of P, with a small neighborhood of P in S is the trace of a regular curve, and we call this curve gamma. We can try to make a picture. If this is the surface S, this is the point P, this is N at P, this is V, then we are considering P, which is a span Vn of P. Actually, this is small p plus capital P. Okay, we parameterize gamma by arc length. Gamma satisfies these two conditions, and this is called the normal section of S at P in the direction V. Now, since gamma lies on the plane P plus capital P, then also gamma second lies on P, and it is necessarily and the gamma second 0 is necessarily orthogonal to gamma prime 0 equal to V, that is it is parallel to n at P. Why? Because n at P is orthogonal to V. This implies that the curvature is exactly the length of this vector. This formula is true because the curve is parameterized by arc length. So let's write something. Gamma is parameterized by arc length. And we have that the gamma second orthogonal coincide with gamma second, where orthogonal means orthogonal component with respect to V. Now, this is also equal to the absolute value of gamma second 0 inner product of gamma second, inner product and of P, because I told you before that these two vectors are parallel and this has length 1. But this one is exactly the second fundamental form at V in absolute value. And this is the end of the proof. Okay, let's recall the fact that this is the normal curvature if length of V is equal to 1. So we can introduce some new notation. Now suppose that gamma is one of the curves in the family used in the proof. Suppose also that it is parameterized by arc length. Then this implies that the acceleration vector A is gamma second 0, is orthogonal to gamma prime 0, which is V. Okay, we proved before that the normal curvature is the normal component of the acceleration vector. But this one is exactly Kn according to the notation I introduced a few minutes ago. Then this implies that I can write down the following formula. A equal to Kn multiplied n at P plus something else multiplied by R9TV, where R90 is rotation in TPS. Precisely is the rotation by an angle of 90 degrees in the direction that is counterclockwise with respect to the orientation. In other terms, R90 of V is nothing but the cross product of the normal vector at P and V. Why I chose this vector? Because this says that the acceleration vector is always orthogonal to V. So I can decompose this as the sum of two terms. Both of them are orthogonal to V. Why? Because n of P is normal vector at P, which is orthogonal to this vector, which belongs to TPS. And the reason why I chose this vector is that I need a vector which is orthogonal to V. And this term here is not enough because this is just the normal component. This is the normal component of A in the direction of n of P, but in general there would be some other component. The corresponding coefficient is denoted by Kg, and it is known as geodesic curvature of S of gamma at P. Maybe it's a good idea to make a picture. So if this is the surface, this is P, for example, this is N of P, this is V, this is R90 V, and use another color. Suppose that this is gamma, then suppose that I need another color, but I have only 3 of them. So let's use the white one. Suppose that this is the acceleration A. What this formula says is that A has one component which is parallel to N of P, and one component which is parallel to this red vector. Here I am assuming that V and N of P belongs to the blackboard, and the R90 at V is orthogonal to the blackboard. So I can decompose A as the sum of this vector here plus a vector which is parallel to N of P, and I don't sketch because otherwise this picture becomes more confusing. What I can indicate on this picture is that this is the length of this vector, it is Kg, and the length of this vector is the length of this vector here, change of sign. Or maybe it's less confusing let's write just kn. So the length of this vector is exactly kn, because this is a vector of length 1. Clearly, since the length of this vector is k in this case, then if I take the length of this vector here, I get the square root of kn squared plus kg squared. So this is another formula you should memorize. It is clear that the absolute value of kn is smaller or equal to k. So the absolute value of the normal curvature has an upper bound. What about the geodesic curvature? We have that there is no upper bound for the geodesic curvature. Precisely, we have proposition 4.12, which says that all real numbers are attained as values of kg at P for curves gamma in the family described before. We will prove this result later, probably. The reason why this result is true, it is intuitively clear. If the curve gamma looks like this, where this part is, for example, I'm zooming in, is, for example, a piece of circle of a very small radius, then you have that the acceleration vector becomes very long. This means that kg becomes very long. Sorry, kg becomes very large. Anyway, we will prove this result later. Now let's talk about the geometric characterization of the Gauss curvature. Let's start by studying the sign of the Gauss curvature. Okay, by definition, K at the point P is the determinant of the matrix representing the Weingarten map. So we wrote this way. Now, when we studied the orientation preserving isomorphisms between subspace of dimension 2 in R3, we have seen that the sign of the determinant of a linear map tells us if this linear map, which is assumed to be an isomorphism, is orientation preserving or reversing. Precisely using the material of section 3.4, we have the following. Kp is positive if and only if Wp is orientation preserving, negative if and only if Wp is orientation reversing, zero if and only if Wp is not an isomorphism. But we can say more. Precisely, we have proposition 4.13, which says that let S be as usual an oriented regular surface and let P be a point of S if K at P is non-zero, then there exists a neighborhood of P in S restricted to which the Gauss curvature, the Gauss map N defined on S with values in S2 is a diffeomorphism onto its image and it's not finishing, and furthermore Kp is positive, respectively negative, if and only if n is, or maybe let's write Gauss map, the Gauss map is orientation preserving, orientation reversing, respectively, with respect to the given orientation of S and the outward pointing orientation of S2. Okay, how to prove this result? Okay, first of all, let's observe that we have this identity The first two is just definition. What is interesting is the last one. Why this is true? That the determinant of minus dnp is equal to the determinant of dnp. This is true because the matrix which represents this operator, this map, is of order 2, and this means that the determinant does not change sign, even if you change the sign of each entry. This implies that we can reformulate what I wrote before about WP in terms of DNP. So I can write KP is positive, negative, if and only if DNP is an orientation preserving orientation reversing isomorphism. I just copied what I wrote before. Instead of writing WP, I wrote DNP. Now, what is the problem we have? The problem we have is that we have to prove that N is a diffeomorphism. But here we have only that the differential of N is an isomorphism at P. The idea is to use the inverse function theorem for surfaces. It's the theorem 3.35. This theorem, which uses this hypothesis, precisely we are using the first part, ensures that N is a diffeomorphism between neighborhoods of P and N at P. Now, the second thing to do is to prove that this is a diffeomorphism not only between neighborhoods, but so we want to prove that N is a diffeomorphism between S and N of S. How to do this? We use proposition 3.52. I want to recall this proposition. So, proposition 3.52 a diffeomorphism F between connected oriented surfaces is orientation preserving if and only if there exists P in S such that DFP is orientation preserving. So this result says that if you want to prove that a diffeomorphism between connected surfaces is orientation preserving, just look at this derivative. But this is exactly our conclusion if we use if we replace F with N. We already know that DNP is orientation preserving because the Gauss curvature is positive. So if we take smaller neighborhoods of P and N of P, I can suppose that they are connected, and then we have that this is true, that the Dn of P is orientation preserving, and this means that the original diffeomorphism N is also orientation preserving between S and S2 with their orientations. The orientation for S is a choice of N. Instead, the orientation for S2 is the outward pointing normal unit vector. Now let's try to make a picture. Let's erase this part. So let's sketch a picture of a surface having positive Gauss curvature. It's something looking like this. Let's consider a small neighborhood of P. And let's take a small closed simple curve like this in this neighborhood. Let's draw also the value of N, values of the Gauss map n at points of this curve. So for example, we get 1, 2, 3, 4, 5, 6, 7, and 8. Let's give some number. 1, 2, 3, 4, 5, 6, 7, and 8. Now, this is S2. Approximately. And I want to sketch the values taken by this map on S2. They are now there are too many arrows, so this is 1, 2, 3, 4, 5, 6, 7, and 8. And I want also to sketch the corresponding small loop to which the tips of these 8 vectors belong. I will try, even though maybe it's a bit confusing now. It should be something like this. And if we move from 1 to 8 along this curve, we move in this direction on S2. So this is the case when we have K at P positive. What happens instead if we have a surface with K at P negative? This is a point where the Gauss curvature is negative. Once again, we consider a small loop contained in a neighborhood of P. And we consider the values of the unit normal vector field to this surface at 8 points. What we get is this. So 1, 2, 3, 4, 5, 6, 7, and 8. This picture is a bit confusing, but I hope that you understood what I'm doing. So what is the situation now on S2? Now the image of the Gauss map N corresponding to the vector marked with the number 1 is this. For the vector marked with the number 2 is this. So this is 1, 2. Then I have 3, 4, 5, 6, 7, and 8. What is the loop that I get if I consider the curve joining the tips of this vector? Is this. And now observe the fact that if I move on this loop moving from 1 to 8 this way, I move on this loop from 1 to 8 in the opposite direction this way. So this is the graphic illustration of the fact that if Kp is positive, then we have that N is a diffeomorphism which preserves the orientation. Instead, in this case, we have that N is a diffeomorphism which reverses the orientation. And now I want to give the geometric interpretation to geometric interpretation of the absolute value of K at P. In order to do this, we use a proposition uh, 3.60, which says that if F is a diffeomorphism, between regular surfaces, and R is a polygonal region of S1, then f of r is also a polygonal region. In S2, and the area of f of r is the double integral over r of the area distortion of df dA. Okay, from this formula we got the following. If r is small enough, and P is a point of R, then we have that the area distortion of F, this is approximately equal to the area of f of R divided by the area of R. This formula follows from this one. Why? Because if R is very small, then you can approximate the right hand side as the product of the value of the area distortion at P times the area of R. And you get immediately this formula. Now let's use this proposition with use the proposition with f equal n from S to S2. If you do this, what you get that the area distortion at P, that is the absolute value of the Gauss curvature, is the area of n of R divided by the area of R approximately. So essentially the Gauss curvature in absolute value can be interpreted as a ratio between areas. And now the last result I want to present is the following. It's proposition 4.14. So let S be a regular surface. Please observe that I did not write word oriented because we don't need it. And let P be a point of S. Then if K at P is positive, then a sufficiently small neighborhood of P in S lies entirely on one side of the plane P plus TPS, except for P. Remember that when I write P plus TPS, I mean the translation of TPS by the vector position of P. This means that the origin of TPS has been translated and coincide with the tip of the position vector of P. If Kp is instead negative, then every neighborhood of P in S intersects both sides of P plus TPS. Let's give the idea of the proof. So up to using a rigid motion, up to using a rigid motion, of R3, we can suppose that TPS is spanned by the vector C1, E2. And that neighborhood of P in S equals the graph of a smooth function f. If you want to have more details about what I'm doing here, please look at the proof of Lem 4.5, page 200. Then what happens if we compute the curvature of the graph of a function f? This is given by this formula. And the result of the lemma now is a consequence of the second derivative test. So if Kp is positive, then we have that P is a local maximum or minimum. In this case, the surface looks like this. Or like this. Locally. Instead, if K at P is negative, then we have a saddle point, and this means that the surface looks like this. And in this case, TPS up to a translation will look like this. So every neighborhood of this point intersects both sides of P plus TPS. Okay, I think that for today it's enough. Thank you for your attention.